There is a certain hype around deep learning, and it has also affected language technology a lot. So what is deep learning and why should we care? According to Chris Manning, one of the leading figures in the field of natural language processing, deep learning can be defined like this. Deep learning is basically the use of neural networks to learn generalizations from data, and in particular the use of large multi-layer networks that increase the capacity of the model. Such artificial neural networks are inspired by the function of the human brain with respect to their hierarchical structure of connected neurons. Deep learning is currently the most successful approach in machine learning in many fields, including computer vision and natural language processing. But let's come back to the general idea behind language technology. Our task is to find appropriate models that can perform language understanding and language generation, similar to what humans can do. The idea with learning-based approaches is to rely on language data and machine learning, such as deep learning, to infer such a model. In deep learning, we apply neural networks for this kind of machine learning to encode observable data into numeric representations in high-dimensional vector space. And similarly, a decoder can map such representations back into language output. The latent representations we learn reflect the understanding of the system and encodes linguistic properties and semantic information, which can be used, for example, as an intermediate layer in neural machine translation. Let's have a closer look at the building blocks in neural natural language processing. As we have said, we rely on vector-based representations. Positions in the corresponding vector space then reflect the semantics to be learned from the data. Neural networks are used to learn functions that operate on vectors, to manipulate them into the desired form, or to extract scores that can be used to make proper predictions. The simplest form is a mapping from context-independent words to so-called word embeddings. This can be seen as a lookup table of lexical items to some semantic representations in high-dimensional space. Now the question is how to use that information captured in such vectors in sequential data such as language input. One way would be to simply concatenate or average them or to sum them. But this does not take into account that there are certain dependencies between the words in context. Therefore, a new structure is required that incorporates sequential dependencies between linguistic units we observe. Recurrent networks implement a straightforward structure for this that iterates over items to accumulate information, taking the entire history into account. The result of this procedure is a representation of the entire sequence with respect to the order of the items as they appear in the context. Using the basic building blocks, we can now extend the architecture to include even additional layers, to run in both directions, for example, or to stack all the components together like Lego bits. And growing complexity increases then the capacity of the model and enables more advanced abstractions. A powerful alternative to the recurrent setup is the so-called transformer architecture, which is behind all major large-scale language models that we can see, that people talk about. Here we replace the recurrent connections with trainable attention patterns that reflect the dependencies that are found in sequential data. So after that introduction of some of the basic blocks in natural language processing and neural approaches to that, we have finally a few words about training such models. The computational graph represented by the network structure implements a mathematical equation that can be optimized using an objective function, defined by the data that provides the supervision for training the network parameters. This is then done in iterations using an algorithm that is called backpropagation, which pushes adjustments through the network step by step. In NLP, various objective functions can be used to train language models, including tasks that learn to predict words in context, classify text, or translate sentences from one language to another. Training is a heavy process in deep learning, as networks typically contain millions of open parameters. Only modern hardware makes it possible to enable efficient training through massive parallelization. Also note that such complex models require a substantial amount of data, and reducing that requirement is an active research field. So, summarizing the success of deep learning in NLP, we can say that their main advantage is the reuse of pre-trained components that can be shared and applied to fine-tune generic models for specific downstream tasks. The ability to pick up generic knowledge from data that can effectively be transferred to new tasks is the beauty of the approach. The ability to integrate datasets of different modality or different domains covering different languages makes them flexible and powerful, and new extensions are constantly proposed. So stay tuned, and thank you for your attention.